Hey everyone, up next we're going to talk about how to graph our rational functions using a pretty simple and straightforward 3 or 4 step procedure. So in the setup, we're going to suppose that our rational function f of x is just written as, or can be expressed as, p of x over q of x, where p and q are our polynomials with no common factors, meaning our rational function is in a simplified form. And so the first step we want to take in helping us put together the information we need to graph our rational functions is finding the intercepts of our rational function. And so there's going to be two kinds of intercepts we can find for our rational function, and these are the same two types of intercepts we try to find for pretty much all of our functions, our x-intercepts and our y-intercepts, or our horizontal and vertical intercepts. So remember, whenever you want to find the x-intercept of a function, you set that function or y equal to 0 and then solve for x. Well, if we set our function f of x equal to 0 here, we get 0 is equal to p of x over q of x. So remember, whenever you want to find an x-intercept, you just set your function or y equal to 0 and then solve for x. So we would end up here with 0 is equal to p of x over q of x. But the only way we can get an output of 0 from a quotient is if the numerator is equal to 0. So if we want to find the x-intercepts of our rational function, we just set our numerator or p of x equal to 0 and solve that equation. And so the other type of intercept that we are often interested in is our y-intercept or our vertical intercept, and that's found when we set x equal to 0. So if we set x equal to 0, we just have to evaluate our function f of 0 to find our y-intercept. Both sets of intercepts are important, although the x-intercepts are going to be a little bit more important, and we'll talk about why once we are trying to put all this information together. So the second step in finding the information we need to sketch a graph of our rational functions is finding the asymptotes of our rational function. That is, if any asymptotes exist for our rational function. So the first types of asymptotes we discussed trying to find for our rational functions were those vertical asymptotes. And remember, the vertical asymptotes were caused by division by 0 for our rational function, which happens when our denominator is equal to 0. So we can find the location of any vertical asymptotes if they exist for our rational function by solving the equation when is q of x equal to 0. So solving p of x equals 0, or the numerator set equal to 0, helps us find x-intercepts. Solving for when the denominator, or q of x, is equal to 0, helps us find vertical asymptotes. So the next thing I want to put in our asymptote category is going to just be our end behavior. And I'm putting that in there because the end behavior for our rational functions is often these horizontal asymptotes at y equals 0 or some other constant, or sometimes we get a non-horizontal asymptote like a linear asymptote, slant or oblique asymptote, or even some kind of quadratic or other polynomial asymptote. And so we're not going to re-go through that analysis for finding the end behavior of a rational function or recopy those 3 cases down. You can just go back to our previous video to see that. But we want to remember, for finding the end behavior or horizontal asymptote of a rational function, they're always found by comparing the degrees of p and q together, the degree of the numerator compared to the degree of the denominator. And so our third and just about final step for graphing our rational functions, besides actually drawing the thing itself, is what we call the test point step. And so what we don't know at the moment is if we have some type of asymptote, whether it's horizontal or slant or whatever, how are we approaching it? Are we approaching it from above? Are we approaching it from below? That's exactly what these test points are going to help us figure out. And so we're going to pick an x value between and beyond each of our x-intercepts and vertical asymptotes, plug those test x values into our function, plot the corresponding points, and with those points on our graph, in addition to our x-intercepts and our asymptotes, we'll be able to put everything together and figure out how do we approach these vertical asymptotes and the end behavior of our function. All right, so let's go ahead and see how our procedure is going to work for graphing this example. So in this example, we want to graph the rational function f of x, which is defined as 3x minus 3 in the numerator and x minus 2 in the denominator. So let's go ahead and start gathering our information in our procedure over here, starting with the x-intercepts. So to find the x-intercepts, we have to solve when is p of x, or our numerator, equal to 0. And we just add 3 to both sides and divide by 3 to figure that out, or you could factor the 3 out. Either way you go about doing it, you should find that the solution to 3x minus 3 equals 0 occurs when x is equal to 1. So we know our x-intercept is at the point 1, 0. So in the first part of our procedure over here, we also have listed finding the y-intercepts. I'm going to save that step for later, because what I'm going to end up doing, and this is what is often the case, is I'm going to use x equals 0 or y-intercept as one of our test points. So that means we are ready to move on to the second step of our procedure over here, identifying the asymptotes and end behavior of our rational function. And so remember, our vertical asymptotes occur when we get division by 0. So we have to set our denominator equal to 0 and solve for x. That's pretty easy in this example. It's going to happen when x is equal to 2. All right, so we're not done with our second step, because now we have to investigate the end behavior of our rational function. And remember, this is done by comparing the degrees of our numerator and our denominator against each other. And so in the numerator, we have 3x minus 3. In the denominator, we have x minus 2. Both of these are degree 1 polynomials. So the degree of the numerator is equal to the degree of the denominator. And when we were in that case, I think that was our second case in our previous list, when the degree of the numerator is equal to the degree of the denominator, we have a horizontal asymptote, because the degrees are equal, and the horizontal asymptote is always given by y is equal to some constant number, right? That describes a horizontal line, and that constant number in this case is the ratio of the leading coefficients, 3 divided by 1, or just 3. So as x gets really, really big, positive or negative, our function is going to have to slowly approach this horizontal line at y equals 3. All right, so because we're running a bit low on board space here, I'm going to go ahead and do the third step and the graphing step all together. This is actually a pretty good way to go about doing it, because it can help you kind of pick some of your test points. So before I actually start picking these test points between and beyond each x-intercept and vertical asymptote, I'm going to go ahead and graph the information that we already know about the function on our set of axes here. So we know our x-intercept is occurring at x equals 1. We have a vertical asymptote at x equals 2. And so remember, a vertical asymptote will cause our function to approach positive or negative infinity depending on the direction. And our function will never cross a vertical asymptote. The last piece of information we have found that is not yet on our sketch is that we have a horizontal asymptote at y equals 3. 1, 2, 3. Let's say y equals 3 is right about there. And so we're pretty much always, when graphing, going to indicate these asymptotes using a dotted or hashed line. That's what I've done here in pink. And so now we're really ready to find our test points to figure out how do we kind of draw in our rational function. We know we have to go through this point, so we're going to be coming down from this horizontal asymptote, hit that point and bounce back up, or cross through that 0 and down towards negative infinity. Or on this side, we're going to come up from negative infinity and approach our horizontal asymptote at y equals 3, or come down from positive infinity and approach our horizontal asymptote at y equals 3 from above. This is exactly the point and why we need these test points. And so we need test points between and beyond each x-intercept and vertical asymptotes. I always like to work from left to right finding my test points. So the kind of feature that we have furthest to the left is our x-intercept at 1. So beyond our x-intercept at 1, to the left of it, are all these values less than x equals 1. The idea is we only need one test point to really determine the entire behavior of our function in this region over here. So we know we're going to have to be coming down from our horizontal asymptote in order to hit our x-intercept at x equals 1. But our test point should verify this. It doesn't matter which x value I use to the left of x equals 1, but I'm going to use x equals 0 because it'll also give us our y-intercept. So if we plug x equals 0 into our function here, we get negative 3 over 2, or 1.5. And so that helps me plot this point on our graph. So we know we have to approach our horizontal asymptote at y equals 3 as we head to the left. Then we're going to have to cross through these 2 points that we found. So next what we have to figure out is how does our rational function behave on this interval between our x-intercept at 1 and our vertical asymptote at 2. You can go back to the idea of multiplicities to assist you in doing this, but I think test points are a little bit more straightforward and sometimes quicker and less likely to make a mistake when using. So now we need to pick a test point between x equals 1 and x equals 2 to determine the behavior of our rational function on this interval. So 1.5 is right between those values. We could even pick 1.0001 if we wanted to, but 1.5 is probably a bit nicer to plug in. The output that we end up getting is -3, so -3 would be right down about here. But what this test point is really telling us is not where that next point is going to be, but how does our graph behave as we approach this vertical asymptote from the left-hand side. We are decreasing without bound, going down towards -infinity. So now we've figured out how most of this rational function behaves. We have one more region to test, and that is to the right or beyond our vertical asymptote at x equals 2. So any test point to the right of x equals 2 will work here. So let's go ahead and use x equals 3. If we plug 3 into our function up there, we end up getting 6 as the output. So if we're trying to keep our scale accurate, this output of 6 should be right about here, right? This was an output of 3, so twice as high should be about an output of 6. And so now, how do we use this dot to finish graphing our rational function? Well, we know that as we head off to the right, as x approaches positive infinity, our function has to approach this horizontal asymptote at y equals 3. So we're going down and becoming horizontal as we move off to the right. Then we have to also approach our vertical asymptote at x equals positive 2. And since our function is already positive and there's no other place for it to change signs, it has to approach this vertical asymptote by going up towards positive infinity as we move to the left. So one last note to end this example with is, remember, we are really just doing a rough sketch of these rational functions. There is sometimes going to be behavior we do not yet have the tools to determine. So what I mean by that is, for certain rational functions, we may have some weird behavior like we come up above a horizontal asymptote and then come back down it. We do not have to worry about finding that behavior. That really requires the tools that we would develop in a class like calculus. So your sketches don't have to be perfect. They don't have to look exactly like what comes out of a graphing calculator, but you should have at least this much information as a minimum.